Welcome to this PDH Online video course on An Introduction to Fire Protection Engineering for Buildings. Today's instructor will be Mr. Paul Geyer. Mr. Geyer is a registered civil engineer, mechanical engineer, fire protection engineer, and architect with 35 years of experience designing buildings and related infrastructure. For an additional 9 years, he was a principal staff advisor to the California legislature on infrastructure and capital outlay issues. He is a graduate of Stanford University and a fellow of the American Society of Civil Engineers and Architectural Engineering Institute. And now, here is Mr. Paul Geyer.
I want to put some emphasis on one or two words in that title. The first one is introduction. That's what this is. This is an introduction to fire protection engineering. It's not for engineers who have been involved in fire protection work for many years and are looking for a real in-depth, detailed presentation. That's not what this is. This is really targeted at all of the members of the building design team who are aware that there are almost always fire protection issues in any building design project, but that's about the extent of your exposure to it so far in your career. And this hopefully will give you some initial feel for the terminology and the technology and the approaches that are used in fire protection engineering. So I hope that's what you had in mind when you signed up. And also I will be talking just about buildings. There, of course, can be other situations in the infrastructure area where there are fire protection issues, but I'm just talking here about buildings. Here is kind of what I will be talking about today, the chapters in the book, you might say, or how I will be chopping up the information. There is a massive amount of detailed information about fire protection engineering. It's the National Fire Protection Association and the International Code Council have cranked out codes and codes and codes and codes about how to deal with every conceivable fire protection issue that you can have. And it's obviously impossible to even scratch the surface with all of that body of knowledge in a short little webinar like this. So what I'm going to be doing is just hitting on some points that will give you a feel for the kinds of things you need to pay attention to when you're addressing a fire protection issues in a building. First of all, so chapter 1, you might say, I will be talking about building materials and design. And this is just a mishmash, if I may say, of a lot of different observations about things you need to pay attention to in building design. And so that's kind of the nature of what I'll be talking about there. Chapter 2, if you will, I will be talking about water supply for fire protection. There are different ways, obviously, of putting out a fire, but by far the most common one is using water. And not too many people think about water supply. Is the water supply going to be adequate for the building that I'm designing? You just kind of naturally assume that the water utility, that pipe out in the street, is going to have enough water in it to deal with a fire in your building. But actually, you do need to address the water supply issue, as does your local water utility. Chapter 3, I'll be talking about fire extinguishing systems. And of course, again, water is the most common one, but there are others, and you will, in certain situations in a building, you will use one of these other extinguishing systems. Fire alarm systems, Chapter 4. Have a few comments on fire alarm systems and what they do. I'll be talking about, in Chapter 5, special occupancies and hazards. There are a zillion special occupancies and hazards that are defined in the fire codes. and I'll just be talking about some of the more common ones that you're more likely to have contact with in your building design activities, and the things that you will think about or do when you're faced with one of those special occupancies, so to speak. The Chapter 1 will cover, to a degree, the kinds of things you see enumerated here, all of the pieces that you put into a building, what the structural system is, and what the finishes are, and the HVAC system, the electrical distribution system, so on and so forth. The water chapter, or the discussion, my comments on water supply. The two main categories that you will be looking at are water supply for sprinklered buildings, those that have an automatic fire sprinkler system in them, and those buildings that do not have an automatic fire sprinkler system in them. And whether or not you have fire sprinklers in your building is mandated by code, and so you can make an engineering decision that even though it isn't mandated for your building, you're going to go ahead and put in an automatic sprinkler system. Then the other main category is the demand for water in buildings that do not have an automatic sprinkler system. The fire extinguishing systems, these are the fire extinguishing systems that we will take a quick look at, and I'll just try to give you a feel for where you would use them. Fire alarm systems do essentially three things: detection, they detect a fire, they report the fire to typically the fire department, and that sets the firemen into action to come and put out the fire at your building. And then evacuation systems, which are the local alarms that tell the occupants of the building that there's a fire somewhere and they need to get out of the building. These are some of the more common special occupancies and hazards that I'll have a couple of comments here and there on. Okay, this is a point that I like to make whenever I'm giving this webinar. Fire protection engineering is almost completely code and regulation driven. There's almost nothing theoretical that you're going to encounter in fire protection engineering. But the only thing that's theoretical, if you will, is the hydraulic design of the pipes for an automatic sprinkler system. There you're using the stuff that you learned about the flow of fluids in pipes. But other than that, in fire protection engineering, it's all code and regulation driven, and the key to success is being familiar with those codes and knowing which one of the multitude of them that you should grab and look up what you're supposed to do in a given situation. And as a matter of fact, just an aside type comment for any of you that may perhaps harbor an interest in getting registered in fire protection engineering, if your state offers it, is the key to success is just making sure that you have all those codes with you when you walk in to take the exam. Because and being familiar with those codes, where everything is, because that's what the fire protection PE exam is an exercise in looking things up in the fire codes real fast. Another background comment I like to make is that fire safety is a very highly regulated enterprise, and of course the codes are part of that regulation undertaking. The fire safety and structural safety are the two big concerns that building departments always have when checking a set of plans. And so you're going to get close scrutiny when you submit some building plans as far as fire safety is concerned. A unique, if you will, aspect of this review process, the plan checking, is that typically not only are your plans going to be reviewed by the building department, where the reviewers are going to be either professional engineers or perhaps younger engineers or perhaps even just experienced building inspection technology people, but your plans are also going to be reviewed by the fire department. And the fire department reviewers they're not trained engineers, they're not experienced designers or experienced in construction. They're firefighters. And they've had a bit of training in plan review, but that's about it. So sometimes this can get a little testy when your plans are going through the fire department. And you have to just, I would say, be sure that use your diplomatic skills in dealing with the fire department to get your plans through. And be sure to explain as clearly as you can what your thinking is and what your authorities are that you're citing for what you did on your plans. And hopefully that'll smooth things out when your plans go in for review. Now, again, I want to place emphasis on, before we get into the meat and potatoes here, on the comment I made at the start that this is only an introductory overview of fire protection engineering. It's not a design manual or a code collection or a code treatise or anything like that. And so don't refer to this presentation for actual design guidance. You must always go to the appropriate codes and regulations applicable in your jurisdiction where your project is located. And the things you see on these PowerPoints are for illustration only. First thing you should start out with when you've got a building and you're preparing the plans and specs for it is you should do what you do in all of the technical disciplines when you start out, whether it's the HVAC system, whether it's the structural system, whether it's electrical distribution, whatever. You should start out with a design analysis. And this is a good roadmap for the plan checkers, both in the building department and in the fire department, is a well put together design analysis document. So these are the elements that you would typically include in the design analysis, a code analysis. What are you building your building out of? What kind of occupants are going to be in the building? How does the code classify it? One thing that I stay away from in this webinar is talking too much about the specifics of the various classification systems in the codes. And the reason I do that is the codes are constantly changing every time they get revised, which is frequently. They change things around. So you just need to think generically here as I'm going through this. Talking about what the codes have told you are the requirements for fire-rated walls, fire-rated doors, dampers, etc., things like that. That guides the plan checker. Now, fire-rated walls and fire-rated doors, this brings a fundamental concept underlying fire protection engineering, and this is life safety. The purpose of fire protection engineering is not to prevent the building from being damaged or to prevent the building from being burned down. It's nice if you can achieve that objective, but the fundamental objective of fire protection engineering is life safety. And everything that you're doing is focused on alerting the occupants of the building as early on as possible that there's a fire in the building and guiding them to get them out of the building expeditiously. And so to do that, you build barriers that permit some degree of isolation of the location where the fire takes place and keeps that separate from the egress routes, how the people are going to be getting out of the building. And you do this by constructing barriers, i.e. walls, floors, ceilings, and in different locations building them of different levels of fire-resistive construction. Anyway, these are all the items that you should kind of include in your design analysis. Okay, now we're slipping into Chapter 1, and this again is just a selection of kind of random comments about building materials and design. There is, in the code arena, there unfortunately, even though there, a number of years ago there was a strong effort made to reduce the number of code writing agencies in the U.S. to one. Unfortunately, that objective was not fully achieved, primarily because NFPA decided that it did not want to participate in this coming together exercise. And perhaps that might be because NFPA produces many, many codes, and they're a source of income for NFPA. And if they were to have entered into an undertaking with the other members of the International Code Council, that revenue stream would probably disappear for them. So anyway, you're going to need to be looking at both the NFPA codes and the International Code Council codes. The code requirements are a function of the type of construction and the occupants, what kind of occupants are in the building. And this you, I'm sure, already know. Also, a point to keep in mind is separation between buildings. And this is an important consideration in fire protection engineering, and it is mandated for different kinds of buildings in different kinds of situations. The point being that if a fire breaks out in one building, you don't want that fire to jump over to another building and set the other building on fire. So if your building is of a more fire-resistive type of construction like concrete, then the code will allow you to have your building closer to other buildings because the concrete is more fire-resistive than wood, say. So separation between buildings is important and is dictated by the codes. And you just have to look it up in the code, probably the IBC, International Building Code, and comply with those separation requirements. And if your building is too close to another building, the code may dictate that, for instance, you construct the separation wall of having a high level of fire-resistive construction, and perhaps to extend that firewall, separation wall, a certain distance above the roof line. The point here being that the roof is a very vulnerable element in a building in the event of a fire. That's because the vector of the fires is vertically, and the roof gets a lot of stress from a fire. And you don't want the fire to break out of the roof, because that's how fires spread from one building to another. Debris blows over, things like that. So the fire-resistive construction of the roof is a very important element in fire protection engineering, as is the separation walls if your building is close to other buildings. The codes are going to mandate that certain walls or partitions be of a higher fire-resistive construction. And this is driven by the underlying principle that what you want to do is maintain the integrity of the egress routes in the building. That means the corridors, so that people can get out of the building in the event of a fire. And so the codes will say that, well, your ordinary partition walls between offices can be of 1 hour fire-resistive construction, but the walls and ceiling in the corridor must be of 2 hour fire-resistive construction. That means, in theory, the walls will hold up for 2 hours, allowing the occupants 2 hours to get out of the building. Now, the fire-resistive construction, or how do you determine the fire resistance of a certain construction, wall construction that you are thinking about using, like 2x4s at 16 on center with one layer of half-inch chipboard each side, or maybe steel studs at 16 on center with 2 layers of 5/8 fire-rated chipboard both sides. Well, the way that these many, many different kinds of wall and ceiling and floor constructions their fire ratings is determined is simply by test, and the tests are undertaken by an independent testing agency, usually Underwriters Laboratories, sometimes Factory Mutual. The Underwriters Laboratories grew up out of the insurance industry as a result of a very tragic fire that took place in Boston, Massachusetts back in the early part of I think it was in the 20th century, in a nightclub or something like that. And there was a lot of loss of life. There was no entity in the country that addressed the issue of fire protection standards. And so the insurance industry, because the insurance industry didn't want to pay claims, set up Underwriters Laboratories to test the fire-resistive construction or capabilities of different construction sandwiches for walls, ceilings, floors, that sort of thing. And if the code dictates that a certain wall needs to be of 2-hour fire-resistive construction, you need to keep in mind that that also means that any doors or windows in that wall have to be of that construction, of that same level of fire-resistive construction. And doors and window assemblies are tested in the same way by Underwriters Laboratories as the basic wall construction is. And then the doors have a label on them that says this is a 1-hour fire-resistive door, or a 2-hour, or a 4-hour, or whatever. Same with window assemblies, usually with glass with windows. About the only thing you can do with the glass is to use wired glass, and that holds the glass barrier together for a longer period of time. Another important consideration is the air conditioning system in the building, because it has been learned that the air conditioning system is a good pathway for fire to move from where it breaks out in the building to other areas in the building. And it's not so much the flames that are the real threat as far as the air conditioning system is concerned, but it's the smoke. And when a fire breaks out in one area, you don't want the smoke to get to other occupied areas, because that's a big life safety hazard. And so if you have an air conditioning duct, for instance, that passes through an exit corridor, then you have to do things like put fire dampers in the air conditioning duct at the point where it passes through the wall into the 2-hour rated corridor. And then in the event of a fire, a fusible link typically melts, the fire damper automatically closes and is of such a construction that it will maintain its integrity for 2 hours and keep the smoke from moving from one area to another. Also, as far as HVAC systems are concerned, the state of the art that has been learned and put into place with air conditioning systems and is mandated to greater and lesser degrees with buildings of different sizes and construction is smoke control systems in the air conditioning system, so that in the event of a fire, like one of the basic things that is done is to automatically turn off the air conditioning fan, so that the fan is not forcing the smoke around the building to other occupied areas. And in the more advanced systems that are mandated for larger and more sophisticated buildings, is that through a strategy of duct modifications and automatic dampers and fan controls, in the event of a fire, the primary fan that is moving the air conditioning air around the building is maybe shut off, or a second fan will come on, and with the duct configuration and the automatic dampers and the fan controls, the air conditioning system switches to an exhaust mode and exhausts automatically the air from and the smoke from the location in the building where the fire broke out. And that's something that mechanical engineers have to pay particular attention to. Means of egress, again, the fundamental principle that you want to get the people out of the building. Well, this is where the exit signs and so on and the alarms that go off come into play. And these are dictated primarily by NFPA 101, the Life Safety Code. And that dictates where the exit signs need to be located, how they need to be illuminated, and then in recent decades it has become there has been an awareness developed that some occupants of the building may be handicapped. They may be visually handicapped, blind, deaf, things like that, and so you need to have other supplementary alarm strategies that will provide, like for deaf people, a blinking strobe type light automatically comes on, and the deaf person sees that and knows he has to leave the building. And then audible alarms for blind occupants. And all of this is mandated by codes, and the principal one that you go to is NFPA 101. Smoke, as I indicated, is a big hazard in fires. More so, it's now recognized than flames as far as life safety is concerned. And so the finish materials in buildings, the wall coverings, the carpets, the ceiling system, are now manufactured much more fire-resistive material than they used to be, and they have a lower smoke development rating. And so that, again, is all by and large mandated by codes. And the roof coverings for the roof, again, the roof is a very vulnerable part of an element in a building in the event of a fire, and the codes mandate certain levels of fire-resistive construction for the roof structure. How are these fire-resistive characteristics determined? Again, it's Underwriters Laboratories testing them, or factory mutual. Okay, another concept that is important as far as the roof is concerned, and really for the whole building, is accessibility for firefighters. In the typical fire situation, assuming it's a building that does have an automatic fire sprinkler system, there are two ways to put the fire out. One is with the automatic fire sprinkler system, and the other is the firefighters. And so with their hoses. But the firefighters have to have access to all of the building in the event of a fire breaking out somewhere. And in particular, they need to have access to the roof of the building, because one of the first things they do is go up to the roof and hose it down and keep it wet so that the fire does not break through the roof, for the reason that we already commented on, that you don't want the fire to hop from one building to another. So the way this is accommodated in a building is by providing a fire-resistive route for the firefighters to get to where the fire might be. Now, the easiest example to visualize is a high-rise building, and the channel for the firefighters to move to where the fire is and up to the roof is the stairwells. And that's why you always see stairwells constructed with a very high level of fire-resistive construction, poured-in-place concrete or masonry walls. And that is the channel that the firefighters have available to them to move from outside the building up to the 5th floor where the fire is, and put the fire out with their hoses, or move up to the roof and keep the roof wet. This is one of the factors that the fire department will be checking closely, and there may be local special little things that the fire department mandates that you do before they will approve your plans. Also, along with this access issue, is access to the building for emergency vehicles, particularly the fire engines, but also the ambulances and this sort of thing. And again, this is all mandated by code, and you just have to look it up. In a typical building, again, I'm talking about a multi-story building, you have either a wet pipe or a dry pipe fire riser in the building. And the way things work is on the outside of the building is a connection that connects to this vertical riser, which typically runs vertically in the stairwell. And in the event of a fire, the fire pumper truck will drive right up to the edge of the building where this connection is, and they stretch out a hose to the hydrant in the street, connect one end of the hose to the hydrant, the other end to the pump in the pumper truck, and then the output from the pump connects to the vertical fire riser. And this is necessary in buildings over some certain size, or height rather, because the pressure of the water in the street isn't adequate to get it to the top of any high-rise or even mid-rise building. You have to supplement that pressure, increase the pressure using the pump or pumps in the pumper truck. And so the water is pumped into the vertical riser, rises up in the stairwell. At each floor, there is a connection where the firefighters, after they have climbed up the stairs, can connect their hoses, and that gives them a supply of water to fight the fire on that floor using their hoses. That's kind of the basic schematic there. Let's see. We talked about the primary challenge with the air conditioning system, and that is that it left to its own devices, an air conditioning system will be blowing the smoke from where it's generated in the building all over the building very quickly, and that is a major life safety threat for the occupants. And so you have to prevent that using automatic dampers, fire or smoke dampers that close automatically in the ductwork depending upon where the fire breaks out, and also through the use of fan controls, duct configuration, and dampers, switching the air conditioning, the HVAC system from its normal function to that of an exhaust system to exhaust the smoke directly out of the building from the location where it's being generated within the building. Okay, Chapter 2. That was just a very quick run through some things that you need to pay attention to in selecting the materials for the building and the design of the building. And there you'll need to spend a lot more time with your codes to really get up to speed on that. Now let's move here to this Chapter 2 and look at water supply, which is something that, as I say, you don't tend to think about when you're designing a building. You just assume that there's going to be enough water out there in the street, in the city water line, to provide fire protection for your building. But that's not necessarily the case. How do we know if we've got enough water to put out a fire at our building? The method that is used to determine if the water supply is adequate and who is going to make that determination varies from jurisdiction to jurisdiction. It may be that the building department will do it. It may be that the fire department will do it. It may be that the water utility will do it. And it may be that the building designer needs to do that calculation, if you will. The methodology that we'll take a quick look at here is one that is used by the most experienced entity in the U.S. and perhaps the world in the business of designing buildings, and that is the Department of Defense. Now, don't get turned off by that. There's nothing governmental or military or anything like that about this method, and it's just a good, solid engineering guidance. And it's a very simple methodology that's used. The first one we look at is the situation where the code mandates or you make a decision that you want to have an automatic fire sprinkler system in the building. And so this is the methodology that this DoD approach uses to determine if the water supply is adequate. A simple little table like this illustrates it. In the column on the left-hand side is the occupancy classification of the building. Now this varies, the terminology changes every time codes get revised, but more or less you know that the occupancy classification runs from a light hazard up to extra hazard. And the code specifies what kind of uses and what kind of occupancies fall into the various categories. And so you're going to need water for the automatic sprinkler system, and you're going to need water for the hose stream. The hose stream is the water that is used by the firefighters to put the fire out. In this methodology for the automatic sprinkler system, for the lightest hazard of occupancy, this methodology specifies that the design density of the water from the sprinkler system is, in this case, 0.10 GPM per square foot, on up to the most hazardous occupancy in this illustration, extra hazard group 2. The design density is 0.40 GPM per square foot. So that all looks perfectly logical. More hazardous the occupancy, the more water per square foot you put on the fire. And that's design density, GPM per square foot. What is the square footage figure? That's called the design area, and you see that it is 3,000 square feet for all of the classifications of the hazard. And that intuitively probably looks a little strange. You would think it would be greater design area for the more hazardous occupancies. But the thinking behind it is that what you want to do in the event of a fire is to confine the fire to a certain area and not let it grow beyond that area, and you put it out before it gets beyond that area. And so that design area that in this system is used is 3,000 square feet that you are undertaking to not let the fire grow larger than 3,000 square feet. And so that's why the design area remains the same. So the GPM is just the design density times the design area. In the case of light hazard, 0.1 times 3,000 square feet, or 300 GPM. Then for the hose stream allowance in this methodology is what you see in the fourth column from the left. So many GPM, light hazard 250 GPM, extra hazard 750 GPM. That's the water that's needed for the firefighters' hoses. And you add the two together. In the case of light hazard, 300 plus 250 equals 550 gallons per minute. And what's the duration of time for which that flow must be available? And it is in this methodology what you see in the column on the right, from 60 minutes up to 120 minutes in the extra hazard categories. So the thinking behind it all is that in the case of light hazard, you've got 550 gallons per minute supplied for 60 minutes, and after that the fire is out. That's the thinking. In the extra hazard, it's the extra hazard group 2.4 times 3,000, which is 1,200, added to the hose stream of 750 gives you 1,950 GPM for 120 minutes. And that tells you if you have enough water for fire protection purposes at your building. And you then, if you did the calculation, you give that information that information goes to the water utility. The water utility has their methodologies to see if their system of distributing domestic water around the community is adequate to supply this quantity for this period of time. And if the answer is yes, then you just get your fire water from the utility. If it turns out that the utility comes back and says, no, we can't supply that quantity of water, then what you have to do is you have to store water on site for fire protection purposes. And this is not that uncommon. It's particularly with warehouses. Warehouses are a particularly hazardous type of building because you have typically so much fuel in them, stuff that burns. So they can have a very high requirement for water for fire protection purposes. And so sometimes when you're driving around in an industrial area, you'll see a warehouse-like building with a big tank outside, and that probably has fire protection water in it. So if the local utility can't provide the quantity of water that you need to protect your building, then you're going to have to store water on site. So that was a quick look at a very simple, but that has been used over and over and over and over again with all of the many types of buildings that the Department of Defense has built over the years. And it's what is used and works. Now, then we can take a look now at the second category of buildings, and those are the ones that do not have an automatic fire sprinkler system. Okay, so now we're looking at the situation where the building does not have an automatic fire sprinkler system in it. Here is the methodology that the Department of Defense has used for a long time. It's a very simple little point system, and the factors that are taken into consideration are what you see here. And the way it works is if your building, the first consideration is response time by the fire department. How far away is the fire station? And in this approach, this methodology, if the fire station is less than 2 miles away, your building gets 2 points. And if it's more than 2 miles away, 3 points. If your building of the various types of construction, wood, steel, concrete, masonry, etc., that the codes define all different ways, but ranging from the more flammable type of construction, which is wood, up to the highly fire-resistant type, which would be concrete. If yours is a type 1 building, which is the more fire-resistant type of construction like concrete, your building gets 1 point. If your building is a wood construction, your building gets 5 points. And you're totaling up these points. Number of stories, single story, 1 point. 2 or more stories, 2 points. That seems to leave a lot of building configurations unaddressed, like a 20-story building, but this approach has proven to work. The building floor area is taken into account. If it's 7,500 square feet or less, your building gets 1 point. More than 40,000 square feet, 5 points, and then all in between. Separation distances from other buildings, more than 60 feet to the next nearest building, your building gets 1 point. Less than 20 feet, your building gets 4 points. Maximum hose layout for the first 3 stories, 180 feet or less, 1 point. More than 230 feet, 4 points. Hose layout is from the hydrant to the pumper truck, from the pumper truck to the roof of the building, at least up to the 3rd floor. And you add up all of these points, and demand for water for fire protection purposes is then determined from this simple table here, figure 3. You have the occupancy classifications, again, on the first column on the left. The fire flow required, and again, this is the hose stream. This is what the firefighters need. There's no sprinkler system. If your building got 6 to 10 points in that simple little evaluation we went through, then the fire flow is what you see in the first column there, 750 GPM up to, at light hazard, up to 2,500 at the most hazardous occupancies. And the more points your building gets, the more water you need to have. So if you had a total of over 16 points, light hazard would be 1,500 GPM, up to the extra hazard 5,000 GPM. And what is the duration over which that GPM must be available? That's given in the 3 columns on the right. 6 to 10 points, the duration is 60 to 150 minutes. On up to over 16 points, it's 120 to 240 minutes. And that's the system. And it's simple, it's straightforward, and it's proven. But again, whatever you have to do with your building is going to be dictated by your local building department and fire department. For non-building application or installations, again, this is Department of Defense stuff, talking about petroleum oil storage facilities, oil tanks, gas tanks, things like that. The fire flow required depends upon the diameter of the tank, ranging from 500 to 1,500 GPM, and the duration required is 240 minutes. You might be thinking, well, why is only the tank diameter of consideration here? Why not the tank height or depth? Well, the reason is that with a fluid storage fire risk, what burns is just the top surface area of the fluid, and it doesn't matter how deep it is. The only part that's burning is that part at the top. So that's why depth of the tank is not taken into consideration. And another illustration here in this figure 5 of how DoD handles multiple tank installations. Okay, now we're moving to chapter 3, if you will, fire extinguishing systems. How do you put the fire out? And the systems are what you see here, and we'll touch briefly on each one of them. The most important one is the, I don't know whether to say it's the most important one, but the most common one is the automatic sprinkler system. In other words, water. And so we're all familiar with fire sprinkler systems in buildings and the piping that's running around. And one of the challenges, and this is about the only place that any theory comes in at all in fire protection engineering, is how do you size the pipes that are carrying the water running around in the building. And the situation you've got is you've got the water that's being supplied by the local water utility and right at the exterior wall of the building, and that water is being supplied at, say, 50 psi. Well, and then we just looked at the design densities that were required, how many GPM per square foot of water were needed to be put on the fire. And the fire design area is the 3,000 square feet in these illustrations here. And all fire sprinklers are rated by the manufacturer. And so the manufacturer in the catalog will say, well, my sprinkler head will discharge so many GPM per square foot over a 15 by 15 square foot area or 20 by 20 square foot area, as long as you provide it with water at a pressure of at least, say, 20 psi. So you've got 50 psi coming in, and you need to have 20 psi where the fire breaks out. Now, for purposes of doing this calculation, the location where you assume the fire is breaking out is the most hydraulically remote location in the building, and typically that's the most geographically remote location in the building, remote from the point where the water enters the building. And so you've got 50 psi coming in, 20 psi you need on the fire, and so you can lose 30 psi due to friction loss in the piping. Well, step number one is first of all, you'll do a layout of the piping and make some assumptions, which is quite easy to do, about the pipe sizes. Generally speaking, there's nothing in a fire sprinkler system, in the distribution system on a given floor, that's larger than about 2 inches, maybe maximum of 2.5. But the vast majority of the piping is probably going to be 1.5, 1.25, 1 inch, and finally 3/4 inch. And so you do a preliminary layout and say, okay, I'm going to assume 2-inch pipe from here to here, and then it necks down because some of the water is discharged in other branches, and it necks down to 1.5 inches, and then down to 1 inch, and then down to 3/4 inch. And so you've got a preliminary layout, and you convert all of that piping to equivalent lengths of straight pipe, and using a table like you see here. That converts fittings into equivalent lengths of straight pipe. So, for example, a regular 90-degree elbow, 1-inch pipe size, that elbow is the equivalent of 5.2 linear feet of 1-inch pipe, and so on and so forth for everything in the distribution system, the elbows, the T's, the valves of the different types, and strainers, and so on and so forth. So you convert your preliminary layout to equivalent linear feet of straight pipe, and then you use a table that looks like this, which relates pipe size to pressure drop per 100 feet at different flow rates. So you might say that if you add it all up, and you can use, say you had come up with 3,000 equivalent linear feet. Well, since you want to have, you can take 30 psi pressure drop between the entry to the building and where the fire is, that would work out to, if you had 3,000 linear feet, that would work out to 1 psi per 100 feet of equivalent feet of straight pipe. And so you just select a pressure drop that will work for your preliminary layout. So you would select, in this simple illustration here, 1 psi of loss due to friction in the per 100 feet. You can tolerate that with your preliminary layout. And then the water flow rate is, for the different sizes of pipe, is what you see with the different colored lines there. And so you go through, and using this table, you would calculate the pressure drop between where the water enters the building and where the fire is. And if it turns out that you've got too much pressure drop, that means you're going to have to increase the size of some reaches of your pipe. So you might increase a 1.5-inch pipe reach to 2 inches, say. So this is how you size the pipes in your distribution system. And I mean, there are different ways, of course, that you could do it, but this is the simple way, and the way you do it all the time, really. Now, I was talking earlier about the wet or dry standpipe. This is the pipe, again, using the illustration of a multi-story building, 5, 10 stories high or whatever, and the fire protection water enters the building through a connection on the outside wall and rises vertically in a pipe, a standpipe, vertically up to the roof. And at each floor, you have a connection that looks something like this. And this is what your sprinkler system on that floor connects to. And these are the elements of this connection. You see, starting as soon as you tee off of the riser, you have an indicating type valve. That is one that it is apparent at a glance that it is open or closed. could be a rising stem valve, in which case if the stem is up, the valve's open. If the stem is down, the valve's closed. Or it could have a dial on it that says open and close. That's very important because you want your maintenance people to be able to quickly, when walking through the building, always be able to glance over and make sure that someone hasn't snuck in and closed off the valve, in which case the entire floor would not be protected by the automatic sprinkler system on that floor. There's a check valve to keep the water from the sprinklers piping on a given floor from it flowing backwards into the riser. You see a water flow switch there. That's the key element in the alarm system. When that switch senses that water is flowing in the pipe, that means that one or more of the sprinklers on the floor has opened, which means that there is a fire on that floor. And so that sends the signal to the alarm system, electrical or electronic alarm system, to sound the local alarms and send the report of the fire to the fire department. And then there's the supplemental piping there for testing the piping on the floor, to drain the piping on a floor for maintenance purposes. And so anyway, this is more or less what you have at each floor on a multi-story building. Now that's the water is being used as the medium for putting out the fire. There are other things you can use to put out a fire. There is a class of extinguishing agents that are called aqueous foam film forming agents, foam systems. And these are used frequently in places like aircraft hangars, places where there's a lot of fuel of some sort, I mean gasoline, diesel, things like that. The reason is that you can't use water to extinguish a fire with some kind of a petroleum fuel like that, because the petroleum fuel is lighter than the water. It will just float on top of the water and keep burning. So these A3F systems were developed in the event of a fire. This A3F, which is a mixture of, I was told one time it's something like beef blood that they get from slaughterhouses. It's mixed with water, and it foams up when it comes out of the nozzles on the sprinkler system. And this foam floats on top of the oil fire or fuel fire and smothers it. And so this is an extinguishing system that is used in those situations where there's a significant risk, like I say, in an aircraft hangar of a fuel spill and it's running all over the floor. And, so this is another extinguishing system. Dry chemical extinguishing systems. Now these are ones that in ordinary day-to-day building design you may well encounter, because these are the ones that you would use typically in a kitchen. And again, the challenge here is that the fires that pop up in the kitchens are grease fires, and the grease floats on top of the water and you can't put the fire out. And the place where these fires are the biggest risk is at the cooking surfaces of stoves and things like that, and in the fume hoods that are exhausting the fumes from the cooking surface. The grease builds up in the exhaust duct, and that grease can catch fire, and in which case, and so what you often typically have is an automatic dry chemical system that senses a fire on the cooking surface or in the exhaust duct and discharges a dry chemical that smothers the fire. So dry chemical systems are something that you will run into commonly. Carbon dioxide is another good extinguishing agent. It extinguishes the fire by smothering it, by depriving it of oxygen. And the problem, and this is used, carbon dioxide could be used on grease fires, could be used on electrical fires, this sort of thing. The problem with carbon dioxide is, though, that by denying the fire oxygen in the atmosphere, it's also denying the building occupants oxygen, and so they are put at risk. And so carbon dioxide systems are used only in areas that are not normally occupied by humans, like a transformer vault or something like that. But in those applications, they're a very good system, and they extinguish a fire without doing a lot of damage, if you will, to the area that they're protecting, because like a water sprinkler system can do a lot of damage in a fire, more damage perhaps from water than from the fire itself. The next category is special systems. Originally, they were called Halon 1301 systems that were developed as the computer and the electronics industry came to be important throughout the U.S. And the point here is that, or the objective here, the intent here, is that you do not want to, if you have a little fire break out in a wastebasket in a computer room or something like that, a lot of very expensive electronic equipment, you do not want to discharge water sprinklers because it'll ruin the electronic equipment. And you can't use carbon dioxide because you have humans in the room. And you can't, obviously you couldn't use a foam system. So these gas systems were developed, originally called Halon 1301, which is a proprietary gas, which would reduce the oxygen content in the protected space sufficiently to put out the fire, but not to such a degree that humans did not have time to get out of the space. And they were quite effective at doing that, dealing with that difficult fire protection challenge. However, they were, before too long, found to be an environmental no-no. They're a fluorocarbon or something like that, I forget, and those were determined to be harmful to the atmosphere. So the original Halon 1301 systems have by and large all been taken out of service, but they have been replaced by different gas systems that do the same thing. And so they're typically called generically clean agent fire extinguishing systems. So they're used in areas like computer facilities and so on and so forth. And there are some others categories: wet chemical extinguishing systems, mist systems. The water mist systems are typically used maybe in a tank environment where you've got a liquid in a tank, or it could be a solid in a tank, and they lower the temperature within the tank sufficiently to below the ignition point of whatever the thing is that's burning in the tank. The fire alarm systems, fundamentally, they just do these three things. They detect a fire, and they report the fire to the fire department, and they sound local.
Fire detection systems must conform to the appropriate provisions of NFPA 72, and a development in recent decades is the requirements of the Americans with Disabilities Act, ADA. The detection system needs to be, of course, arranged to inform the building occupants of the fire, to alert them to the need to vacate the building, and then also to transmit a signal to typically the fire department. The detection system must be independent and stand alone and not be part of an integral building security system. The fire detection systems may be connected to a building security system or building management system or an EMCS system, but for monitoring purposes only, and must not rely on any of the components of those other systems for their operation. Fire detection systems, particularly those that are smoke or products of combustion detectors, require significant maintenance routinely. It's important that the detectors are properly installed and maintained, of course, and providing detectors in locations that are not required by code increases the already high maintenance costs of alarm systems and may not be warranted. If a facility warrants protection and criteria does not require detection, protection should be accomplished by a wet pipe sprinkler system. Wet pipe sprinklers provide excellent protection with little maintenance required. The area to be protected by a smoke detection device is defined by NFPA 72, and that area must be reduced by 50% where ceiling fans are used. And this may, of course, require additional smoke detectors for the area being protected. Special occupancies and hazards are defined by the various applicable codes. The NFPA codes in particular define many special occupancies and hazards and mandate what must be done in each of these in great detail. Many of them are rather exotic and you may never have occasion to be involved with them. Some of the more common ones that you do run into frequently in building design, I will have some comments on here. These include food preparation areas such as kitchens, obviously, commercial and restaurant kitchens. Medical facilities are a very significant special occupancy and hazard and require a high degree of expertise when undertaking to design fire protection systems for them. Detention facilities, jails, and prisons are also a significant special occupancy because of the nature of the occupants and the hazards. Electronics and telecommunication facilities are a very important occupancy. And then finally, high-rise buildings are one that has special needs. So I'll have a few comments on all of these. The examples that I'm going to be talking about here are just for illustration purposes only, and for actual building design purposes, the particular codes and other regulatory requirements must be researched and complied with. Food preparation areas, kitchens are particularly common in building design, in restaurants, of course, and other commercial cooking facilities, in medical facilities, in hospitals, and places like that. The particular hazard with food preparation areas is grease, and the fact that, of course, it is combustible and does catch fire readily. It also produces smoke. Kitchens produce smoke, and that can create an issue as far as the type of detection system that is used. In other words, if it's detectors that are smoke detectors or products of combustion detectors, need to be carefully considered because they could be subject to false alarms. And the regulatory driver is for food preparation areas is NFPA 96, ventilation control and fire protection of commercial cooking operations. The extinguishing systems in food preparation areas should be wet chemical or automatic sprinklers installed in accordance with NFPA 96. And the fire suppression system should sound a general building fire alarm and transmit a signal to the fire department or to a constantly monitored location. Areas other than residential units that are provided with residential type range top cooking surfaces need to be equipped with an approved range top extinguishing system that must be connected to the building alarm system to sound the general alarm, and also to automatically shut off sources of fuel and electric power that produce heat to the equipment being protected by that unit. Hospitals and other healthcare facilities are an important special occupancy and hazard because of the nature of the occupants. They are typically, of course, not fully mobile. Many of them are significantly impaired. And the focus on in medical facilities, one major focus is to reduce the risk of fire and smoke starting in the first place. In other words, prevention by selection of particularly finish materials that are not flammable and that do not generate smoke readily. Medical facilities also, because the population includes patients who are not mobile, relies on in many cases on the concept of an area of refuge. And this would be like an elevator lobby on a given floor. And the elevator lobby would be shut off from the corridors and the rest of the spaces with automatic closing doors that would close automatically in the event of a fire. And the strategy is that in the event of a fire, the alarm goes off and the staff at the medical facility will move the patients, and of course they are on movable beds, will move the patients into the area of refuge. The doors are closed and the patients and their attending staff will remain in the area of refuge until the fire can be extinguished by the fire department or the automatic fire sprinkler system. So these areas of refuge are an important strategy in protecting the occupants of hospitals and ambulatory care centers and places like that. With detention facilities, prisons and jails, it's almost the obverse of the typical strategy for occupants of buildings in the event of a fire, where you want to get the people out of the building expeditiously. With detention facilities, of course, the inmate population, your strategy includes not releasing them because that's why they're in jail in the first place. So the strategy is very much to eliminate flammable materials in the detention facility so that fires just don't start. And in the event that fires do start, that the fire can be extinguished with the inmates in place, or as a last resort where they are moved to essentially what would be an area of refuge, as was described when I was talking about the medical facilities. The appropriate regulation code in this area is NFPA 101, and there are requirements for fire areas and construction types, minimum separations in public ways. They require an automatic sprinkler protection system using breakaway type sprinklers. Sprinkler piping in inmate areas needs to be concealed because, like so many things in a detention facility setting, the inmates are constantly looking for things they can use as weapons and so on and so forth. Smoke detection should be provided as required by NFPA 101. And also another reference is the American Correctional Association's Planning and Design Guide for Secure Adult and Juvenile Facilities. And that is a good guide. Also, there needs to be an automatic smoke removal system in cell areas, because the strategy is that the inmates remain in their cells in the event of a fire, and so you need to have a system to exhaust the smoke from those cell areas. In the detention facilities, the general approach in their design, of course, is to provide constant visual supervision of cell areas by the guard staff, and this is a plus, if you will, as far as fire detection is concerned, because the supervising staff are there and can observe if a fire breaks out. And the separation between the cell areas and the place of supervision needs to have a 1-hour fire rated construction. There needs to be a mechanical or closed circuit electrical gang release devices whenever 10 or more locks must be operated to release prisoners. And there are other requirements and best practices as far as prison design is concerned. The interior finish of cells, including padded cells, must be Class A flame spread and must have an SD rating, a smoke development rating, not exceeding 50, in accordance with the methodology in ASTM E84. Part of the overall strategy of maintaining the prisoners in their cells and using finished materials that are not flammable, do not have a high flame spread rating, and do not have a high smoke development rating, so that the prisoners can remain in their cells. The issue with electronics and telecommunications facilities is the risk fire poses to a very expensive electronic equipment, and also what can be very costly data that is stored on the by the data processing equipment. And the objective is to have a fire detection and suppression system that will not damage that equipment and that data. When the computer generation came along initially, some computer rooms were still protected by wet pipe fire sprinkler systems. And so you could have situations where a simple little fire might start in a wastebasket or something like that, a minor little fire, but it would trigger the fire sprinklers to open and dump large amounts of water, potentially on the data processing equipment and on the computers, and of course probably irreparably damage the equipment and cause the loss of data. In response to this threat being recognized, a product called Halon 1301 was developed for the suppression of fires in electronic and telecommunications facilities where there was this high risk. And this was a gas fire suppression system, but one of the concerns with a gas fire suppression system, like CO2, carbon dioxide, could be a gas suppression system. But the problem is that the carbon dioxide is a hazard to human beings in the space, and so it was not appropriate to discharge CO2 to put out a fire in a computer room because of the risk to the human occupants. So the Halon 1301 was initially developed to a gas product that had enough oxygen in it that it was not hazardous to occupants of a space, at least for a reasonable period of time, and it would allow the occupants, in the event of a fire, to get out of the computer room, but then the oxygen content was low enough that it would smother the fire, suppress the fire. And so 1301, Halon 1301 was rapidly adapted as the standard in computer rooms. However, after some number of years, it was determined that the Halon 1301 was it was a fluorocarbon, and that the fluorocarbons were considered to be an environmental hazard if released to the atmosphere. So gradually over time, Halon 1301 systems were taken out of service and replaced by different proprietary gas systems, generally referred to as clean systems, clean fire suppression systems. And so they work in the same manner as the Halon 1301 did, but they do not have this environmental impact consideration. The guiding code in this area is NFPA 75, Protection of Information Technology Equipment. The data processing facilities and facilities with electronic equipment are usually located inside buildings that are protected by a wet pipe automatic sprinkler system. However, generally speaking, you would want to use in the actual space where the electronic equipment is located, clean agent fire extinguishing system. And the power and communication or data cabling installed in spaces above ceilings or below raised floors must be plenum rated or installed in metal conduit. Now, that is because of the smoke generation issue in the event of a in a typical computer room, the underfloor space and the above the ceiling space are both part of the HVAC system, and the concern is, as it always is, about transferring smoke from where a fire breaks out to other parts of the building through the air conditioning system, the air circulation system. And so anything that is installed in those spaces above the ceiling or below the floor must be rated for minimal flame and smoke generation risk. High-rise buildings, of course, are a special occupancy and hazard. The driving code in this area is NFPA 101. There are many considerations in a fire detection and suppression system in a high-rise building, and one of the major areas of concern is circulation. That is the ability to get people out of the building expeditiously in the event of a fire, and to get firefighters into the building expeditiously in the event of a fire. And so the concepts have been developed over many years and are well known. And the circulation, the key element there is stairwells. And the stairwells are the route that the people in the building take to get out of the building in the event of a fire, and that the firefighters use to get into the building in the event of a fire. And so those stairwells need to be constructed of highly fire-resistant materials like concrete, CMU block, poured-in-place concrete. And the detection system in a high-rise building, typically the way it works is there are, of course, fire detectors on all floors, and one of the things that the system does is send a signal to a control panel, a fire control panel that's typically located down at the first floor, either on the outside of the building or on the inside of the building in the stairwell. And this is a location where the firefighter, when he arrives, can look at the control panel and see what floor the fire is on and immediately go to that floor rather than having to search through every floor in the building to find where the fire is. And then, of course, in the stairwell typically is the fire sprinkler riser. This is the vertical pipe that contains the water supply that the firefighter connects to with his hose at the floor when he gets to the floor where the fire is located. The occupancy hazard classification systems defined in the appropriate codes, either NFPA or International Code Council. The nomenclature varies and it kind of changes over the decades, but it more or less looks roughly like what you see here: light hazard, ordinary hazard group 2, and then extra hazard, and then special occupancies. Special occupancies are ones that can't be assigned to a regular classification because of special protection requirements. Examples might be warehouses and aircraft hangars. Warehouses, because of typically the large amount of fuel that is stored, and that means burnable materials that are in typical warehouses. And there are codes, NFPA codes, that address these special occupancies. These next few slides are just a listing of the many codes that are produced by NFPA and to a much lesser extent by the International Code Council and one or two other organizations that are relevant in the fire protection area. Factory Mutual is an important trade or technical or professional organization in the fire protection area. Primarily was developed historically to provide fire protection standards for factories. Cleverly, that's where the name Factory Mutual came from. And then the number of NFPA codes is very extensive. NFPA developed historically, as I believe I got my facts straight on this, there was a disastrous nightclub fire in Boston, Massachusetts back in the early part of the 20th century, and there was a lot of loss of life. And it was due to the fact that there weren't any standards for fire protection in buildings at that time. And NFPA, I believe, was basically started by the insurance industry to establish some standards for buildings so that when they insured them, they would not be taking on any inordinate risk. NFPA has extended over the years to many areas of fire protection, not just buildings, and so their materials are applicable to marine facilities, as an example, boats, things like that. The International Code Council is the other major entity in the fire codes business. In some cases, fire protection requirements have been mandated by law, federal laws as an example. And of course, there are all sorts of rules and regulations that have been established by local and state authorities in this area. But as an example, the United States Code, the federal codes, do get into fire protection issues. So as you can see, and as I think I indicated at the start, the fire protection engineering enterprise is highly driven by codes, and the codes are what you are going to be turning to almost continuously when you are designing the fire protection features for a building. and it would be nice if there were a bit more coordination between NFPA and ICC, but that doesn't seem to be something that's going to take place in the near future.